Welcome back everyone to Module 5 of our software development course. Today we will dive into the second major activity in the software development process, which is software design and implementation. We will begin by defining both software design and implementation, highlighting the key differences between them. Next, we will explore various UML models used in object-oriented design and introduce the concept of design patterns. We will then examine different implementation issues, focusing on those not typically covered in regular programming courses. And finally, we will discuss open source software, including its characteristics and various licensing models. So let's get started. As you are used to seeing me start my videos with a question, here is the one for today. What is the design and implementation phase? This phase is where we create an operational software system, which is a core part of the software development cycle. But to really understand it, let's break it down further and ask another question, which is, what is the difference between design and implementation? Software design is a creative activity where we identify the software components and define how they relate to one another. Think of it as creating a blueprint for the system. Software implementation is a process of translating the design into an executable code using a programming language. It's where you turn the blueprint into a really working product or really working software. And here is an important note to keep in mind. Design and implementation are not entirely separated activities. They are always interleaved. For example, imagine designing a weather station system where you initially decide to use a specific data structure to store sensor data or sensor readings. During implementation, you might realize that the chosen data structure does not handle large data sets efficiently. This would lead you to revisit the design, adjust the data structure, and then continue coding. So you will often revisit the design while implementing the system, making adjustments along the way. I have another question for you in these slides. Do you know what is the most important implementation decision is? It is deciding whether to create a custom application from scratch or purchase off-the-shelf software that can be configured to meet your needs. Choosing COTS often has significant advantages. Cost effective as it reduces development and maintenance expenses. Faster as implementation is much quicker compared to implementing a new software from scratch. And finally, customizable. Many code solutions allow you to tailor them to meet your specific requirements. Let's now cover the object-oriented design topic. Object-oriented system consists of interacting objects, each with its own private state and operation to manage that state. These objects are defined by classes, which specify their structures and interactions. During the design process, we create these classes, defining their structure and behavior. When implemented, objects are dynamically created from these classes' definition. If we compare the object-oriented design with regular structured design, we find the object-oriented design benefits from self-contained objects. This means objects can be understood and modified independently without impacting other objects, and this term known also as encapsulation. One of the major advantages of object-oriented system is their close association with real-world entities, making the design more intuitive and improving both its understandability and maintainability. Object-oriented design process can vary depending on the organization implementing them, but they all share some common activities. Let's go over these activities briefly. First, you need to understand and define the context of the system and its external interactions. These steps ensures that the system is well integrated with its environment. Then you will design the system architecture, which involves defining the structure and organization of the system's component. Then it is important to identify the principal objects within the system. These are the key building blocks that drive functionality. After that, you will develop design models to represent how the system components interact and work together. Finally, you will specify interface, which define how the system components communicate with each other and with the external environment. And I will cover all these activities in details in the following slides. Let's start with the first activity, which is understanding and defining the system context and interactions. The purpose of this stage is twofold. First, to understand the interaction between the system and its external environment. Second, to define the system boundaries and decide how functionality is distributed between the system and other components in the environment. To achieve this, we use two key models. The first one is a context model, which provides a structural view of the system and how it fits within its environment. The second is the interaction model, which offers a dynamic view of how the system interacts with its environment during actual use. These models are very important to ensure that the system integrates seamlessly with its surroundings. So let's look at some examples from the weather station system. This diagram illustrates the relationships between the key entities in the system's environment. It's a block diagram designed to visually represent the association and interaction among these components. The central entity here is a weather information system, which communicates with all other entities in the system. First, we have the control system, which supervise and interact with multiple weather stations. The cardinality here is 1 to many, indicating one control system managing multiple stations. Next are the weather stations themselves, which are distributed system collecting environmental data. Each weather station interact with both the control system and the weather information system. Finally, we see the satellite system, which plays a key role in facilitating communication between the weather stations and the weather information system. The cardinality annotations are also significant in this diagram. So here there is one control system, one satellite system, and one weather station system. But there are multiple weather stations connected to these entities. We see here an interaction model, specifically represented as a use case model, which I'm sure you are already familiar with. Here is how the use case model works. Interactions are shown inside the ellipses, representing the different action or functionalities the system supports. The participating external entities, such as weather station system and the control system, are illustrated as stick figures. This example shows the use case model for a weather station system. Each action, like report weather or restart, corresponding to a specific interaction between the system and its external entities. What is particularly helpful about this model is that each use case is described in structured natural language. This makes it easier for designers to identify system objects necessary for implementation and understand the system's purpose and how it interacts with external components. Now let's move on to the second activity in the object-oriented design process, which is architectural design. In this stage, the goal is to define the overall structure of the system. To do this, we use the interaction details from the previous step and our domain knowledge to shape the system architecture. Apply architectural design principles to guide the system's structures and ensure it meets its requirements. The key steps in architectural design include identifying major components within the system and how they interact, designing the system organization by choosing and applying architectural patterns. Common pattern includes the layered model for separation of concerns and the client-server model for distributed systems. Let's take a look at the high-level architecture design of the weather station software. As shown in the figure, the architecture consists of independent subsystems that communicate through a common infrastructure, which is a communication link. Each subsystem listens for relevant message on this infrastructure, implementing a listener mode, which is a typical architectural system for distributed system. A great example for this in real life is something like Google Home, where devices listen for specific commands broadcasted across a shared network. For instance, if the communication subsystem receives a control command like shutdown, each subsystem detects the command and shuts down appropriately. This design is highly flexible, allowing different subsystem configurations because the sender does not need to target a specific subsystem. Now, if we zoom into the data collection subsystem, its architecture follows a producer-consumer pattern. Here, the transmitter and receiver objects manage communications, ensuring messages are sent and received efficiently. And the weather station object gather information from the instruments and transmit it to the weather information system. The third activity in object-oriented design process is object class identification. This step is crucial but comes with some challenges, which is identifying object classes is not straightforward as it heavily depends on the designer experience and domain knowledge. Here are some key insights to keep in mind. There is no universal method for identifying object classes. The best approach will vary depending on the system and its requirements, and that the process is an iterative process, meaning refinement and the multiple attempts are often necessary to get it right. Throughout the 80s, as object-oriented design matured, uh, several methodologies were proposed to determine object classes. Here are some of the most common approaches. Use a grammatical approach based on a natural language description of the system. Base the identification on tangible things in the application domain. Use a behavioral approach and identify objects based on what participates in what behavior. And finally, use a scenario-based analysis. The object, attributes, and the methods in each scenario are identified. Let's take a closer look at the object classes identified in the weather station system. Object class identification in this system is based on tangible hardware and the data managed by the system. Here we will explore 5 key object classes. First, we have the weather station class. This class provides the system interface and encapsulates high-level interactions, such as report weather and shutdown functions. These interactions could be separated into different classes but here they are centralized within the weather station object for simplicity. Next is the weather data class, which processes weather reports. It collects and summarizes sensors data such as temperature, wind speed, rainfall, and more, sending this information to the weather information system when required. Finally, we have specific sensor classes, including ground thermometer, anemometer, and barometer. These classes corresponding directly to the physical instrument in the system. Each of these classes controls the associated hardware to autonomously collect and store data, which is then supplied to the weather data class upon request. Each class of these sensor classes is designed with methods like get and test to interact with the system, keeping their functionality modular and reusable. Now let's move into the fourth activity in the object-oriented design process, which is design models. Design models are essential as they help us visualize the objects, classes, and the relationship between these entities within the system. This model provides a blueprint for understanding and refining the system's structures and behavior. There are two kinds of design models. The first one is structural model. This focuses on the static structure of the system, describing object, classes, and the relationships between them. And dynamic models, which captures the dynamic interaction between objects during the system operation or execution. To detail these design models, we typically use three UML models types that we already covered last week, which are subsystem models that show the logical grouping of objects into subsystems, sequence models that illustrate the sequence of interaction between objects in a specific scenario, and finally, the state machine model, which represent how objects change their state in response to events. The last activity in the object-oriented design process is interface specifications. Interface specification is important because object interfaces needs to be clearly defined. This allows different objects and components to be designed in parallel without dependency issues. However, it is important to remember a key principle. Designers should avoid specifying how the interface is implemented. Instead, the implementation should remain hidden within the object itself, ensuring encapsulation and flexibility. Another point to note is that objects can have multiple interfaces, each representing a different viewpoint on the methods provided by the object. To specify interfaces, the UML typically use class diagrams, which allow designers to clearly represent the relationships between objects and their interfaces. Alternatively, programming language like Java can be used for interface specification during implementation. In this slide, we see how UML class diagram notation is used for interface specification. When representing interfaces in UML, we use the interface stereotype, which you can see included in the name section of each interface here. Unlike regular class diagram, interface diagram excludes the attribute section, as interfaces focus solely on the methods and behaviors that the object provides, rather than its internal state. For example, the reporting interface include methods like weather report and status report, which return a specific report type based on the input identifier. The remote control interface includes methods for controlling instruments, such as start instruments, stop instruments, and collect data. These methods enable interaction with the system's component while encapsulating their implementation details. This approach ensures that the object implementing these interfaces remain flexible, with the focus on what they do, not how they do it. Interfaces like this play a critical role in designing systems with well-defined interaction between components. Let's now jump to a new topic in the design process, which is design patterns. So, what exactly is a design pattern? A design pattern is a way of using abstract knowledge about problem and its solution. It is not just a specific implementation, but a description of the problem and the essence of its solution. To be effective, a design pattern should be sufficiently abstract, meaning it can be applied to different situations and not just tied to one specific scenario. Design patterns often rely on object-oriented characteristics such as inheritance and polymorphism to define flexible and reusable solutions. In essence, design patterns capture best practice, highlight good designs, and package the experience of solving recurring problems in a way that others can easily understand and reuse. By using design pattern, we can leverage tried and tested approach to create more robust and maintainable design. Let's explore the four main elements of design pattern in the following slides. These elements form the foundation for understanding and applying design pattern effectively. The first element is name. This is a meaningful reference to the pattern, allowing us to easily identify and communicate about it. A good name makes it easier to discuss and document the pattern. Problem description. This explains when the pattern may be applied. It defines the context of the problem and helps determine whether the problem is a good fit for a specific scenario. Solution description. The solution is not a concrete design, but rather a template for solving the problem. It provides a structure that can be used in different ways, depending on the specific requirements of the system. And finally, consequences, which highlight the result and the trade-off of applying the pattern. It is important to understand both the benefit and the potential limits when deciding to use a particular design pattern. In the following slide, I will show you these elements for the observer pattern, which is one of the most popular design patterns. Let's go through the table step by step. Pattern name. The pattern is called observer because it focuses on watching and reacting to change in the state. Problem description. This pattern solves the problem of having multiple displays, like graphs or tables, that need to update automatically when the system state changes. The key is that the system does not need to know about the specific types of displays it is updating. Solution description. The pattern has two types of objects. Abstract objects. We have two of them, the subject that keep track of the state and the observer that react to changes. And concrete object, and we have also two objects here. The concrete subject sends out the updates, and the concrete observer that keeps their own copies of the state, updating and showing the changes automatically. And finally, consequences. The subject does not need to know much about its observer. It only knows their general types. This makes the system more flexible. However, it can lead to some unnecessary updates, and fine-tuning display performance might be harder. Now let's take a look at how the observer pattern works with a real-world example. In the center, we have the subject, which maintains the state. In this case, a dataset represented by values for A, B, C, and D. These values are the source of information that the observer are interested in. On either side of the subject, we have two observers. Observer 1 generates a pie chart display based on the data, and observer 2 generates a bar chart display using the same data set. Here is how the observer pattern functions. The subject stores the state, which is the data, and notify its observers whenever the data changes. When an update occurs, both observers automatically receive the update state. Each observer processes the state and update its respective display format. A pie chart for observer 1 and a bar chart for observer 2. This setup highlights the flexibility of the observer pattern. The subject does not need to know how the observers represent the data. It simply sends updates. This makes it easy to add or modify observer without changing the subject itself. Let's see the class diagram of the observer pattern. This diagram illustrates how the pattern works by showing the relationships and interactions between the key components. At the top, we have the subject class, which represents the object being observed. It provides three key methods: attach observer to add observer to the list, deattach observer to remove observers, notify to notify all attached observer about the change in state. Moving to the concrete subject, this is the specific implementation of the subject. It maintains the actual subject state and provides a method called getState, which observers can use to access the current state. On the right side, we see the observer interface. This defines a single method, which is update, which observer implement to react to state changes in the subject. Below that, we have the concrete observer, which is a specific implementation of an observer. It maintains its own observer state and updates this state using the update method whenever it is notified by the subject. The communication flow works like this. When the subject state changes, it calls the notify method. Notify loop through all attached observer and calls their update method, and then each concrete observer retrieves the update state from subject using getState and update its own state. I hope you understand how this pattern works, and don't forget that the scope of this course is not to discuss this pattern. Most probably you covered something like this in the object-oriented class. If not, please, look at different patterns because it will be very helpful. And the last note that I wanted to add before jumping to a new topic, any design problem you are facing may have an associated pattern that can be applied, such as observer pattern, iterator pattern, decorator pattern, singleton pattern. So you need to be familiar with different patterns. As far as you are familiar with more pattern, you will understand easily which pattern fit in your problem. Let's talk about implementation, which is an essential phase in the software development process. This is the phase where the software transitions from design to become an executable system. While programming is, of course, a key part of implementation, today we are focused on other important implementation issues that are often overlooked in traditional programming texts. These issues include reuse. Modern software development heavily relies on using existing components or systems. Reusing pre-existing code can save time, reduce cost, and enhance reliability, making it a key strategy in efficient development. The second issue is configuration management. During development, multiple versions of software component are created. Without a proper configuration management system to track and monitor these versions, there is a risk of using the wrong component, which can lead to a serious issue in the final product. And finally, host target development. In most cases, production software uh, is not run on the same computer where it is developed. Instead, it is created on a host system and deployed on a separate target system, which might have different hardware or software environments. Managing this transition efficiently is critical to ensure the software works as intended. Now let's discuss each of these implementation issues in more detail to understand the role in the development process. Let's start with reuse in the software implementation. In the past, from 1960s to 1990, most software was built entirely from scratch. Developers wrote code in high-level programming languages, and the only significant reuse came from using programming language libraries. However, as the demand for faster and cost-effective solutions grow, this approach becomes increasingly impractical, especially for commercial and internet-based systems. Writing everything from scratch simply took too much time and was too expensive. To address this, modern system development shifted to a reuse-based approach, where existing software components, framework, or system are used to build new applications. Today, this method is widely um, used across multiple domains, like web-based system where developers use frameworks and APIs, scientific software, which often incorporate existing algorithms and libraries, and even embedded system engineering, where reusable components are becoming more common. This reuse-based approach not only saves time and costs, but also improves the reliability by using proven existing solutions. Let's now explore the different level of software reuse. As shown in this figure, software reuse can happen at different levels, depending on the scope and the goals of your project. Let's go through these levels. The first one is the abstraction level. At this level, you are not reusing actual software, but instead using knowledge of successful abstractions to guide your software design. This involves reusing design concepts, patterns, or ideas that have been proven effective. The object level. Here you directly reuse objects from a library. Instead of writing new code, you pull in pre-existing objects that already perform the functionality you need. This saves both time and effort. The component level. At this level, you are reusing collection of objects and object classes packaged as components. These components provide higher level functionality and can be integrated into your application systems directly. And finally, the system level. This is the most comprehensive level where you reuse entire application system. For example, you might adapt an existing system to fit the needs of your new project instead of building one from scratch. Reuse existing software is a proven way to speed up system development and reduce costs. One of the biggest advantages is that reused software is generally more dependable, as it has already been tested in other contexts. However, reuse is not without its cost and challenges. Let's discuss a few key expenses associated with reuse. The first one is identification and evaluation cost. Time is needed to identify suitable, reusable software and evaluate its compatibility with your system. This process might also involve testing the software in your environment. Purchase cost. If you are using commercial off-the-shelf systems, we know now these systems as COTS, there could be significant cost for acquiring these solutions, especially for large systems. Customization cost. Reusable components often need to be customized or configured to meet the specific requirement of the system you are building. And finally, integration costs. Merging reusable elements, especially when they come from different sources, can be both challenging and expensive. Conflicting assumptions made by different software providers may cause issues, requiring extra effort to ensure everything works together. Now let's move on to the second implementation issue, which is configuration management. It's a critical part of managing software development as systems are constantly changing. Configuration management is the process of managing changes in a software system. Changes might come from new feature, bug fixes, or updates, and without proper management, these changes can cause significant issues. Let's break down why this is so important. Coordination. When multiple team members are working on the same project, it is essential to coordinate their efforts. Configuration management ensures that everyone's changes to shared component are properly synchronized, avoiding conflict or overrides. Access to latest versions. Everyone on the team should always have access to the most recent versions of the software component. This prevents team members from accidentally working on outdated code, which could lead to wasted effort or duplicate work. And finally, reverting to previous versions. If something goes wrong with a new version of the software, configuration management allow you to roll back to a functioning version, minimizing downtime and ensuring stability. Let's now explore the configuration management activities. There are four fundamental configuration management activities. Version management. It includes support for tracking various versions of software components and coordinate development among multiple programmers, preventing any one developer from overwriting others' submitted code. System integration. It provides assistance to developer in determining what component version are used to build each system version, enabling automatic system building through compilation and linking of the necessary components. Problem tracking. It offers a support system for users to report issues and bugs while allowing developers to view who is resolving these issues and when they are fixed. And finally, release management. It involves deploying new software system versions to customers with a focus on planning new release features and managing software distribution. I usually get a question here, which is what is the difference between version management and the release management? The answer is quite simple and easy to remember. Version management focuses on tracking changes to the software during development, while release management is about tracking the functional version of the software that delivered to end users. So let's now explore the third implementation issue. What is host target development? This is when software is developed in a host machine but runs on a target machine. The two machines may have different hardware, operating systems, and supporting software. This model is commonly in embedded systems and mobile applications, where the development and execution platform are often distinct. For example, an application might be developed on a powerful PC and tested on a mobile phone, for example. Here, the PC is the host and the mobile phone is the target. To ensure that the software work on target platform, developers typically use software transfer, which is moving the software from the host to the target for testing, or simulators, which are tools that mimic the target environment on the host machine. Simulators are helpful but can be expensive and are often limited to popular architectures. I want to emphasize here that even the requirements in the host and target machines are not the same. On the development platform, we need tools like an IDE to write our codes, compiler to translate our codes, and testing tools. While on the target platform, we rely on elements like the libraries, related systems, and database to ensure the software functions properly in its intended environment. The last topic I will cover in this video is open source software, an important approach to software creation where the source code is shared publicly and anyone can contribute to it and improving it. Open source software began with the Free Software Foundation, which believed that users should have a freedom to view, modify, and adapt the code as needed. This philosophy drives the entire open source movement. The internet plays a critical role in open source development as developers from around the world collaborate, often as volunteers, to create and enhance software. And what is really interesting that many contributors are also users of the software, which motivates them to improve it. Famous examples here we can find that software like Linux, which is widely used on servers and desktop. This is an operating system. And tools like Java, Apache, MySQL, which are popular choices for developers worldwide. The question we need to ask ourselves now is what are the advantages and the disadvantages of using open source software? As usual, I encourage you to pause the video for a moment, take some time to think about these advantages and the disadvantage, and then resume the video. I will start with the disadvantages. Limited support. No dedicated customer services. Reliance on community support may delay solutions. Compatibility issue. May require extra effort to integrate with existing systems. Steeper learning curve. Some open source tools lack user-friendly documentation or interfaces. Lack of accountability. No guarantee updates or fixes if the community becomes inactive. This is not all the problems. I see also some problems related to the security. And of course, some hidden costs comes from customization. For the advantage, the cost effective, there is no licensing fee, reducing overall software costs. Flexibility and customization. Source code can be modified to fit specific business needs. You have an access to the software itself and to the source code too. Transparency. Access to the source code allow for better understanding and security auditing. Innovation. Rapid improvement due to the contribution from developers worldwide. In this slide, I will talk about open source licensing, which is an essential part of the open source software model. While the source code is freely accessible, its use is governed by a specific license. This ensures that open source software remains protected and used appropriately. The original developer of the software retains ownership of the code and sets legally enforceable terms for its use through the license. This term outlines what users can and cannot do with the software. There are two main types of open source licenses. The first one is a restrictive license. This requires any new system using the open source code to also be made open source. This ensures that the open source philosophy is preserved. The second one is permissive license. This allows the code to be used in different systems, even for commercial purposes. This type of license provides more flexible for companies and developers. In the next slide, I will cover in details these different licenses. Most open source licenses are variant of one of these three models. The GNU General Public License, GPL, mandates that if you use GPL licensed open source software, you must keep your software open source. The second model is GNU Lesser General Public License, LGPL. This is a more flexible version of GPL. It allows software that use open source component to remain private or closed as long as the open source component itself is not changed. If you do change the open source component, you must share those changes as an open source. The third variant is the Berkeley Standard Distribution, or BSD. And this you don't have to share changes you make to the open source code. You can even use the code in a closed system for sale as long as you give credit to the original developer. That's all I have for you today. To wrap up, we covered the key topics of the design and implementation process. We learned about object-oriented design, including UML and the use of design patterns. We discussed the importance of software use and configuration management for efficiently handling changes. Finally, we explored the principle and challenges of open source software and its licensing. Thank you for watching, and I will see you in the next video. Bye bye.